right, here we go. We're gonna start off basically where we left off yesterday. So let's just do a quick recap. This is adding vectors in 2 dimensions. Okay. So what we were just about to do is we're going to take all of the components, or I should say all of the vectors, and just add them up. And what we should get and what we should arrive with is essentially this vector at the end of it all. But as you're going to see, there's kind of a roundabout way to do it. There's an organized way to do it, and there's kind of like a graphical way to do it. So we already did it the hand way, where we measured it with a ruler. We did some scaling and things like that, and we figured it out. This time, we're going to be using the components that we have here. So let's just look at exactly what's going on. We have this V1. This is just vector 1, okay? V1 is made up of an x component of 1 mile and a y component of 0. Can you guys see that? Right? And we haven't talked very explicitly about components. If you can imagine, if a vector goes up at an angle, right, it can be composed of 2 different vectors, right? So just for the sake of making sure that we are super clear, why don't I'm gonna just draw a quick axis. And then, yeah, so let's say we have something that looks like this. We have a vector that looks like that. This vector, right? And if we remember, right? If we add vectors, we can get to this resultant. So let's say we have a vector that looks now like this, and one that looks like, let's use black here. So let's call this A, call this B. So if I add A and B, I should get R, right? And in fact, we would say R is equal to the vector A plus the vector B. And these little lines on top, these are just arrows, right? They just represent that these are vectors. So vectors don't add algebraically. For example, you guys should know this. 3 plus 2, what does that equal again? Oops. That equals 6, right? But for vectors, oh, sorry, 5? Who said 6? For vectors, that won't always be the case. For linear vectors, you can do that, right? When we had something that was like this, so this is like 3, and we had something that was like this, and that, or actually, yeah, we can do that, like this, and this was like 2. Right, we would subtract these, and we would get a vector that is the length of 1. Right, so with 1-dimensional vectors, you can add algebraically, but with 2-dimensional vectors, you can't. Right, and that's actually why we learned the Pythagorean theorem, is so that we can do the actual vector addition. So what I wanted to kind of point out, though, was that, remember, this equal sign means that these two are essentially interchangeable. Okay, so what we're going to do, though, going back to our original problem, is we're going to break every single one of these down to the components, which for us is actually really easy because they're either horizontal or vertical. And then we're just going to add them all up. Okay, so let's actually look at that real fast. So let's say if I take all the vertical ones, right? Let's say I'll take this one. Let's do it over here, right? So I have this one right here, and then I take. How did I want to do this? Should probably actually do it something like here. Actually, no. Let's go back to this way. Let's go this way. So ignore the horizontal ones for a second. If I go like this, I'm going to scooch it over just a little bit so you can see it. Notice that it lines up with the top of this one. And then if I do the same thing here, and again, I'm just going to push it over to the side a little bit so you can see. So they should be on top of each other, but I shifted them just a little bit so you can see. And let's actually scooch this one back a little bit too. So it should be going all the way, oops, to the top. Oh, nope, doesn't want to listen to me. Okay, there we go. Yeah. So notice, if we add the vertical ones together, we get the vertical component, right, or the vertical component of this R vector. If I add the horizontal parts together, I get the horizontal part. So that's all we're really doing. By making this data table, we're just finding the 2 vectors, where if we add them together, we get this blue one. Is that okay? So let's just try that. Let's see what happens, okay? So this is the graphical way. Now let's look at it mathematically. We did this yesterday, okay? So we saw that vector 1 was just plus 1 mile in the positive x direction. Okay? And we can check that. We go back. That is this one right here, right? Plus 1 mile in positive x direction. Then we had vector 2, which is 3.3 miles in the positive y direction. That was just this one right here. And then similarly, we had then vector 3, which is 4.1 miles in the opposite direction, so in the negative x direction. And then, as well, vector 4 is negative half of a mile in the half a mile in the negative y direction. So all we're doing is just we're combining like components. So we added those all together, and we get a vector that is 3.1 miles long going in the negative x direction, and then 2.8 miles long going in the positive y. Right? And if you're kind of looking at how these are related to each other, that's going to give us exactly, let's move these over here, the components to make up this one. So I'm going to adjust the size of this a little bit now. Let's go a spot right here maybe. Take this. So I can tell you with certainty, this horizontal one that I have selected right now, that is negative 3.1 miles long. And this vertical one right here, that is 2.8 miles long. So what we can do now is let's just make a triangle. All right, so I have this one. It says 3.1 miles. Notice, again, I'm no longer keeping the negative because the direction is denoted by the arrow itself. And then I have this other one up here, 2.8 miles. And then that's going to give me a vector r that is the sum of all of our vectors. Oops. And this is what we want to figure out. So can you guys figure out yourselves then how long r is and then the angle that is made right here? And I want you to do that. So take a moment to do that. If you're watching the video, take a moment to do this. I know I can see you right now. Do it. I know you're trying to fast forward. Just do it. Especially you, Michael Forberg. It is, yeah. It's just Pythagorean theorem. So just give people a second. What's up?
I'm just saying, just get the angle.
Try to get the angle as well.
What's the YouTube channel?
What's up?
What's your intro to your channel?
Oh, it's man, I don't have any movie editing software right now, so.
Hey, Ian McNair here.
Hey, Ian McNair here. So great to see you guys. No. You guys ready to learn some physics?
Are you on a platform like Patreon or something?
No. This stuff is crap compared to what everyone else posts. So I can't do any of that like animation and all that. All right, so I think a lot of you got it already. So I'm gonna write out the work and then you're just gonna tell me the answer. So you should have 2.8 squared plus 3.1 squared. Take the square root. What do we get? What do we get? 1/8? Okay, that's fine. We'll just do that. Cool, so that means R is 4.18 miles long. And for the angle, we'll just use these two. So we just use tangent for now. So do the inverse tangent of, 2.8 over 3.1? What do we get for that? 42 degrees. And the last part is we just want to add a frame of reference. So where are we measuring from? Which cardinal direction? North, south, east, or west? Where do we start the angle at 0? Not north. Not east. It should be north of west. It should be north of west. And so this is our full description of our R vector. So let's go back. We measured it before, right? And we got what? We got 4.18 miles here. For the original one, we had 4.3 miles. And I don't think we measured an angle, but it's fine. Kwa pointed out something. Hey, Mr. McNair, if we're measuring every single one of these partial vectors, doesn't that mean that our final answer is going to be a little bit more off? And yeah, that's actually very true. It will be. But in real life, when we'll be given usually numbers with these vectors, not just vectors that we're measuring by hand. And in fact, in this class, we'll almost never measure them by hand. So I'll usually just give you the numbers, and so that'll be usually the most accurate way to do it. Yeah. So this part, super annoying. Just get used to it. This is probably the easiest way to organize everything. Another way that I've seen it done is a person would just take each vector and draw them out. But that's like, I don't know, it's kind of dumb, right? You'll have this one, you had like one like that, and then you just start putting in the numbers, right? This is like 4.4 miles, like, it's not great. So, cool. So let us continue on. This is going to be kind of one of your homework assignments. You're going to have to add one of these vectors. Obviously, sometimes we might have vectors where we have to add them like something like this, and then something like this, and then something like that. Yes, I made a thunderbolt. If you can imagine, if we have something like this, we have to break down every single one of these into their components. And so we're going to talk about doing that right now. Right, this one is made up of one that's like this, one that's like this. This one's made up of one that's like that. One's like that. Notice that all of the components, they're only ever going to be on the x or the y-axis perfectly. Right? And the reason why we're doing that is just by convention. It just makes the math easier. So let's look at components. So we are given, basically, let me zoom in on this now. Ooh, my neck is sore. Here we go. All right. So we're given these. Our R here, this time, oh, I don't want to use red. Let's use R is equal to 15 meters. And it says 60 degrees north of east, so that's 60 degrees here. So basically what we want to do is just draw a triangle. So what we do is we drop down from the tip of the arrowhead here. We just go straight down. And we draw an arrow. So we go. That's one component. That's one component. So we can call this then, to get used to subscripts, we'll call this Rx. And this is, whoops, Ry. So I want you all to take a moment. See if you can figure out what Rx and Ry equal. It's actually I think it's the easiest to find components. Can't use Pythagorean theorem this time. So we need two sides at least. Got to use sine, cosine, or tangent. So which of the trigonometric, all right? Trigonometric, that's what it is. Which of the trigonometric identities can we not use for sure? Sine, cosine, or tangent? Tangent. Tangent is the one you don't want to touch because you need the things that are missing. Does anyone have any ideas? Let's go through it together now. Let me erase this first. So first, let's just start with sine. We know sine theta is equal to, we'll say it's Ry over R for us in this case. So what we're going to do is we're just going to solve for Ry. How do you get R to the other side? Multiply. So we get R sine theta is equal to Ry. That's it. So 15 times the sine of 60 degrees, which is square root of 3 over 2 or something. I don't know. And for cosine, very similarly, right? Let's do the work first. So you have cosine theta equals Rx over R. And using the same logic, we're just going to multiply by both sides. Ooh, that looks so bad. Okay, let's try that again. We get R cosine theta equals Rx. So that's literally, let's plug those in then. So this one we get, it's supposed to be an arrow, 15 sine of 60 degrees. So we get 15 cosine of 60 degrees, which I think is 1/2. So what do these equal? 7.5 for the bottom one, right? We'll say meters. And what about the 15 sine of 60 degrees?
12.9.
Was it?
13.
13?
99.
Oh, 30. Okay, yeah, we'll say 13. Cool. That's it. One thing to keep in mind, maybe add a direction. So RY, we could say that that is like north and this is east. You could also say like in the positive Y direction, or you could literally like you could straight up just do like it's 13 meters up. Right? Whatever, right? We're human beings. Whatever makes sense to you, you can do that. So take a moment, try to do the next two on your own. You're going to follow the same algorithm. You're literally just the hypotenuse multiplied by the sine and the cosine. RY. Ooh, it's not a good color. Let's do purple. Oops.
You could probably put as this part of the video.
What's up?
Probably put as in.
As? Ads. Oh, yeah. Hey guys, don't forget to contribute to the McNair Teacher Fund for underprivileged teachers. All funds just go to me. But only $20 and $50 donations, please. Alright, so I think some of you already got it. Like, if you're not writing it down, it's fine. Because it should not be too difficult, I hope. So this one should be 8 sine of 30 degrees. And that should give us RY, which is going to be 4. You're right. And then it should be 8 cosine of 30 degrees, to give us RX. And what is that? 6.9. Heard someone repeat it. Is that you, Julian? Nothing. All right. What about for this one? This one should actually be very easy because when you have 45 degrees, the components will be the exact same length. So you can just choose to do one of them. So let's just choose to do RX. So that should be 5 cosine of 45 degrees. What is that equal to? 3.5? So Rx equals Ry equals 3.5. We said newtons. What might be important though is keeping in consideration direction. So let's actually even look at this one with Rx. Maybe we should have put 6.9 to the left, and then we have Rx is going to be equal to, I'll say negative 3.5. I'm sorry that this is hard to see. I'll say Ry is also equal to negative 3.5 newtons. Right, and the y and the x are kind of telling you which direction they're going in. Cool. Yeah, sorry that that's like really, really hard to look at. So that's finding components. So in general, if you are adding 2-dimensional vectors, you need to break them down into components. Okay, always, 100% of the time. Let's do a. Do you need to go, Zilali? If you need to go, you're fine. Yeah, that's good. Okay. So let's do a quick example. What if I had something like this? So I have 2 arrows, or 2 vectors. I have one that's like this, and let me recolor this. So one that's like that, and I have another one that is like this, same exact angle. Same exact angle. Do I need to break these down into components? So this is 5, this is like 3. We don't. Why not? We can just add them together. They're in the same direction, so it doesn't matter. So keep this in mind. The fact that we have Cartesian coordinates or an axis that looks like a plus sign, the only reason we have that is because that just makes sense to human beings. We can have axes that look like that. And we can say that that's plus x, and that's plus y. Doesn't matter. It's all just convention. So if you think about it with this one, really what we're saying is, right, we're just denoting a new positive x direction. We say, hey, this is positive x, right? And so now you can add them the normal way you've been adding them, which is algebraically. Cool? So sometimes problems will be easier if you rotate axes. In this class, for now, it's probably not going to be, because we're start off with just one-dimensional kinematics, and so you won't have to worry about that. But when we get to projectile motion, forces, or even later on when we do like electrostatic forces, sometimes it'll be easier to change your axes before you do anything else. So now we're gonna do this guy right here. We have adding angled vectors. Okay, I'm just gonna give you all of the information you need, and then you're gonna just try to solve it. But what we're gonna do first is let's label them. Let's say that this is R1. You want to do R1? Let's do V instead. Let's do V1, V2, V3, and let me give you all the information for that. So let's say V1 is equal to we'll work in newtons. So we'll say that this is 5 newtons. We'll say that's at 60 degrees. At 60 degrees, let me make this bigger for now. It's a little easier for me. What would it be? 60 degrees, what? I'm going to say north of east. And of course it changes color on me. Great. Let's say vector 2. I'm already running out of room. It's a little bit longer, so we'll say it's 6 newtons. We're going to say it's at 10 degrees south of west. Okay? And then we're going to say vector 3 is equal to, oops, sorry, this is the last slide. We'll say, let's make it different. 2 newtons at, let's do 75, no, let's do 85 degrees. Oh no, I changed my mind. Let's do 5 degrees. West of south.
Down to the activity center as you celebrate our Mass Holy Spirit with Bishop Rojas.
So before we go downstairs, I'm gonna take you through the logic.
Students from your classroom, please make sure you secure your classrooms. Students, make sure you.
I'll lock all the doors.
In your third period class. That is where you return at the end of.
If you're watching this video, sorry, there's announcements.
Before dismissal. So again, leave your belongings in your third period class. Do not go to your lockers on your way down to the activity center. Again, at this time, all classes on the first floor of both the Dan Ryan Park building and all third floor classrooms should report to the activity center. Thank you.
So check out what I'm doing right now. This is not how you add vectors, okay? But this is how what you can do to make it easier to visualize them. So what's really nice about this is that I can now label these and break down all the components like fairly easily, right? So let's just do this in red real fast. So this is 60 degrees north of east. So we have 60 degrees, goes like that, goes like that. I'm gonna find, so this is like what, V1? So this will be V1x, or sorry, V1y, V1x. These other ones are really small, so it's a little bit harder to draw. So instead of just drawing them like that, I'm gonna draw them out here. I'm gonna exaggerate them a little bit. So I'm gonna call this V2, and then I'm going to make my own components. So this was a south of west. So I'll call this V2x, V2y, and then I'm gonna draw the other one. Again, really hard to see, so I'm just gonna do it myself. This one's more like, ooh, that's still really small. So I'm actually gonna exaggerate it a little bit so it's easier for me to draw. So this is V3, and then we have V3y and V3x. So now, all I'm gonna do is I'm gonna break these down into the components, and then I'm gonna draw a vector that's going to look very similar. Let's take this one, let's recolor this. Let's make it white. The resultant that I'm going to get, which is the sum of all the vectors, it should look like something like that. Right, so if we're just looking at this vector isolated, this kind of looks like, I don't know, if I was just guessing, be like maybe 3.5 or 4 newtons, maybe somewhere around like 30 degrees above the negative x-axis. So what you want to do, and Yeah, I think what I'm going to have you do, no, I'm not going to have you do it for homework. But I do want you to try to break these down yourselves into components. Right? Make that chart, which I can actually, I'm going to move this out of the way. Actually, we'll do the chart on the next one. Right, so we have all these. Right, we have vector 1, 2, and 3, and then we want to make a resultant R. So we draw, get white out, vector 1, vector 2, vector 3, and then we have R, which is our resultant. Each one of these has an X component and a Y component. Cool. So we can get all of these and we'll find a sum. This will be the X component for our resultant, the Y component for our resultant. We can use Pythagorean theorem. We can use sine, cosine, tangent, whatever. And then we can get our final answer, which will be whatever this vector is. So I want to kind of stress this. We're going to be doing this exact problem like every unit. One time we'll have newtons, sometimes we'll have displacement, sometimes we'll have accelerations, sometimes we'll have other things. So this is a problem you want to get to know and love and like be able to solve in your sleep. If you do that, like life is going to be easy for you most of the time. So every single year, this problem specifically, adding vectors that are angled, is the hardest one. Everyone just you forgets, right? We go to a new unit, and all of a sudden at the end of the unit, we have something like this. Right? So I just want to keep that in your mind. It is very beneficial for you to get to know and love this specific problem. It's going to have different labels, different units, but it's going to be the exact same problem. All right? Sound good? All right, cool. All right, so if you're watching now, we're not going to go over this, so you gotta figure it out on your own. You also have a homework assignment. You have to solve this and come into class on Monday with this completely solved. Okay, bye.